At 9:16 in the evening on June 9, 2026, Pacific Daylight Time, a meteorologist sitting inside the National Weather Service office in Portland, Oregon, pushed a button that sent out a phrase a lot of people in that region have learned to take seriously: Extreme Heat Watch, issued June 9th, in effect from Sunday, June 14th through Tuesday the 16th. The watch covers the Portland-Vancouver metro area, the central Willamette Valley, the lower Columbia River Valley, and the western Columbia River Gorge. Dangerously hot conditions, the bulletin says, with temperatures climbing between 95 and 100 degrees Fahrenheit. That's roughly 35 to 38 degrees Celsius, for anyone doing the math in their head right now. And if you live anywhere near Seattle, Portland, Olympia, or the Willamette Valley, you've probably already felt the air start to change this week. Maybe you noticed it on your phone, maybe a neighbour mentioned it, maybe you just stepped outside and thought, wait, it's only June. So here's the question we're going to spend the next couple of hours with. Is this the start of something we've seen before? Something that, 5 years ago almost to the week, killed hundreds of people across this exact region in a matter of days? Or is this just an early summer hot spell that will come and go, leave a few broken daily records in its wake, and fade from memory by July? Because right now, meteorologists are looking at upper atmosphere data that, in their words, looks eerily similar to the pattern that produced the 2021 Pacific Northwest heat dome. Similar, but not identical. And in weather, that gap between similar and identical can be the difference between an uncomfortable weekend and a regional emergency. Let's set the scene properly, because the next 10 days in the Pacific Northwest are shaping up to be a genuine case study in how a heat event builds. And whether you're watching this from Seattle, from Portland, from Vancouver, British Columbia, or from somewhere on the other side of the planet, say from Ho Chi Minh City, where plenty of our viewers tune in, this is worth understanding. Not because you're necessarily going to feel this heat yourself, but because what happens in the Pacific Northwest this week is a live demonstration of a phenomenon that is becoming more frequent, more intense, and more dangerous across the planet: the heat dome. And once you understand how one forms, you'll start recognizing the signs anywhere in the world, including, as we'll get to later, patterns that touch Southeast Asia. Right now, as of Wednesday, June 10th, the Pacific Northwest Weather Network's most recent map update, taken at 7:42 in the evening Pacific time, already shows the watch in place. The bulletin gives people a checklist: sunscreen, light-coloured loose-fitting clothing, avoid strenuous outdoor activity during the hottest part of the day, find a location with air conditioning, which, and we'll come back to this, is a bigger ask in this region than you might think. And there's a line in there that might catch your attention if you didn't grow up around rivers and lakes. A warning about cold water shock, telling people to wear personal flotation devices if they go swimming, because when the air is in the high 90s and the water is still cold from spring runoff, jumping in for relief can be its own hazard. Meanwhile, just one day before that watch was issued, on Tuesday, June 9th, broadcast meteorologists in Portland were already talking about the first heat wave of the summer arriving right on schedule. One digital meteorologist described it as the hottest weather of the year so far, with afternoon highs expected to climb into the lower 90s on Saturday, then push into the upper 90s on Sunday, with some locations potentially crossing into triple digits. That's 100 degrees Fahrenheit or more, about 38 Celsius, for a region where the average warmest day of the year in Seattle sits around 94 degrees. Numbers like that aren't just warm. They're approaching the kind of territory that in recent history has only shown up during genuinely historic events. Now, if you're newer to this channel, you might be thinking, okay, it's summer, it gets hot, what's the big deal? And that's a completely fair question. The big deal is this: the Pacific Northwest, and we're talking about the strip of land running from Northern California up through Oregon, Washington, and into British Columbia, nestled between the Pacific Ocean and the Cascade Mountain Range, is one of the most heat-unprepared regions in North America, not because the infrastructure is bad, but because historically it has never needed to be hot weather infrastructure. Seattle's climate is famously mild, cool, grey, drizzly. A huge percentage of homes in this region were built without central air conditioning, because for most of the 20th century you simply didn't need it. Summer nights cooled off, the ocean kept things mellow, and then came the last week of June 2021. We're going to spend real time on 2021 in this video, because you cannot understand this week's forecast without it. But for now, here's the headline version, just so the stakes are clear from the very first minutes of this video. In late June 2021, an extraordinarily powerful dome of high pressure parked itself over British Columbia, Washington, and Oregon. Temperatures didn't just break records, they shattered them, by margins that meteorologists almost never see. Portland, Oregon hit 116 degrees Fahrenheit, Seattle hit 108, and the small town of Lytton in the interior of British Columbia hit 121.3 degrees Fahrenheit, that's 49, 6 degrees Celsius, setting the all-time national heat record for Canada 3 days in a row before the town was almost entirely destroyed by a wildfire that ignited the very next afternoon. The British Columbia Coroner's Office confirmed 619 heat-related deaths during the most intense stretch of that event alone, and broader estimates for the full event across British Columbia, Washington, and Oregon range from roughly 800 confirmed excess deaths up toward 1,400 when you include less certain figures. Researchers at UCLA later ran the numbers and concluded that an event of that magnitude, even accounting for the warming climate we're already living in, should statistically occur somewhere on the order of once every 10,000 years. And it happened 5 years ago, in late June. So when meteorologists this week start pulling up European model, that's the ECMWF, the European Centre for Medium-Range Weather Forecasts, one of the most respected forecasting models on the planet, and they start talking about 850 millibar temperature anomalies running 14 to 16 degrees Celsius above normal for the days ahead. And when they say those anomaly numbers are, in their words, in similar territory to 2021 at the mid-levels of the atmosphere, you can understand why that gets attention. Not panic, attention. Because there's a crucial piece of this puzzle that, as of this recording, is still missing. And we're going to spend the next stretch of this video explaining exactly what that missing piece is, why it matters so much, and what would need to happen for this week's heatwave to tip from uncomfortable into historic. But before we go further, let's actually build the picture from the ground up. What is a heat dome? Why does the atmosphere do this? And why does the Pacific Northwest, of all places, seem to keep finding itself in the crosshairs? Picture the atmosphere as a giant river of air that flows, generally from west to east around the globe. This river has bends in it. Meteorologists call these troughs and ridges. A trough is a dip in that river, where the flow sags toward the equator, often bringing cooler air and storminess. A ridge is the opposite, a rise in that river, a bulge of high pressure that can extend many kilometers up into the atmosphere, sometimes reaching the altitude of 18,000 feet or higher. When a ridge forms and then, critically, gets stuck, when it stops moving, when the broader pattern around it locks it in place for days at a time, it behaves like a lid clamped over a pot. Air underneath that lid sinks, and when air sinks it compresses and compression heats it up. The same basic physics that makes a bicycle pump warm to the touch when you use it. That sinking, warming air also suppresses cloud formation, because clouds need rising air to form. So you get day after day of cloudless skies, with the sun able to heat the ground without interruption, while the ridge above prevents any of that heat from escaping or being replaced by cooler air moving in from the ocean. That's the heat dome. A stuck ridge acting as a lid, baking everything underneath it for as long as it refuses to move. In 2021, the ridge that set up over British Columbia was, according to the meteorologists who study these things, the strongest ever measured in that part of the world. We're talking about an anomaly in the 500 hectopascal geopotential height, a technical way of describing how unusually puffed up a layer of the atmosphere was that exceeded anything in the historical record for North America going back to 1979, when this kind of satellite-based record-keeping really got reliable. One peer-reviewed study described the surface temperature anomalies during that event as exceeding 4.5 standard deviations from normal. If you're not a statistics person, here's the plain language version. Events that far outside the normal range are, under most statistical assumptions, not supposed to happen within the lifetime of human civilization, and yet it happened, in 2021, in a place known for its rain. So now, fast forward to this week, the European model is showing a ridge. The 850 millibar anomalies, remember that's the layer of atmosphere about a mile above the ground, above the morning marine layer, and the low clouds that usually blanket Puget Sound, so it gives forecasters a cleaner read on the character of the air mass moving in. Those anomalies are running 14 to 16 degrees Celsius above normal for the period of June 15th through 17th, and as one meteorologist covering this for My Northwest put it directly, and we're paraphrasing here, the anomaly numbers themselves are actually in similar territory to 2021 at those mid-levels of the atmosphere. But, and this is the key sentence of the entire forecast discussion right now, what's missing, at least so far, is the kind of historic upper-level ridge that made the 2021 heat dome the killer that it was. The current model runs show a ridge. They do not show that ridge. Not yet, anyway. Think of it this way. Imagine two ovens. Both are preheating. Both are showing similar temperatures on the thermometer inside right now, but one of them has a door that's about to swing shut and stay shut for 5 straight days, while the other one's door might only stay closed for a day, maybe 2 before something opens it back up. The air inside both ovens might look the same in this exact moment, but what happens over the following 72 hours depends entirely on that door, on whether the ridge aloft locks into place, or whether it's a more transient, glancing kind of heat that builds, peaks, and then gets pushed out by the return of the normal onshore flow from the Pacific. And this is genuinely, as of the time this video was researched, an open question. The forecast models agree on the broad strokes. Hot weather is coming, the watch is justified, temperatures in the upper 90s and possibly into the triple digits are likely for parts of the interior valleys and the Columbia River Gorge over the weekend of June 13th through 16th. Where the models diverge is on persistence. Does this ridge dig in and become a multi-day record-shattering event the way 2021 was? Or does it deliver 1 or 2 genuinely hot days and then get nudged along by the jet stream with what meteorologists call onshore flow, cooler, moister air coming in off the Pacific Ocean, arriving to break the heat by midweek? We'll come back to that forecast question later with the most current numbers we could find, including the specific hour-by-hour breakdown for Portland's forecast point through the weekend. But first, we need to actually understand 2021 in real depth. Not just the headline numbers, the 116 in Portland, the 121 in Lytton, but what it actually felt like on the ground, what the science later discovered about why it happened, and why some researchers think it's a preview of something the Pacific Northwest is going to see more and more of as the planet continues to warm. Because here's the thing about heat domes that makes them different from almost every other natural disaster we cover on this channel. An earthquake gives you seconds of warning, if that. A volcanic eruption can build for weeks but often surprises everyone with its timing. A solar storm gives you maybe a day, 2 if you're lucky, between the moment a coronal mass ejection leaves the sun and the moment it slams into Earth's magnetic field. But a heat dome you can see coming. The models start flagging it 5, 6, 7 days out. The signature shows up in the upper atmosphere before it ever shows up on a thermometer at ground level, which means that, unlike almost any other phenomenon we talk about on this channel, a heat dome is a disaster you get to watch arrive in slow motion. And that slow motion quality is exactly why it's so dangerous, because by the time people feel it, by the time it's uncomfortable enough to change behavior, the dangerous part has often already begun. So let's go back. Late June 2021, and let's walk through what actually happened hour by hour, day by day, because the details matter enormously for understanding what we should and shouldn't be worried about this week. The heat wave officially began on June 25th, 2021, and by most accounts wrapped up by July 7th, though the most extreme, most dangerous days were concentrated in a much tighter window, roughly June 26th through June 30th. In the days leading up to it, forecasters had already flagged something unusual happening high in the atmosphere over the North Pacific. A disturbance in the polar vortex, that ring of cold air that normally sits locked over the Arctic, had split apart. Pieces of that disturbed vortex drifted south, one of them settling over the Bering Sea, and from there, it extended down along the west coast of North America. What followed was what meteorologists call an omega block, named because the shape it traces on a weather map resembles the Greek letter omega. A low-pressure trough, then a high-pressure ridge, then another low-pressure trough sitting side by side and refusing to move. The high-pressure ridge in the middle of that omega became the heat dome. By June 26th, temperatures across interior Washington were already climbing into territory that would have been considered a peak summer day in a normal year, except this was barely the beginning. June 27th, a Sunday, saw Seattle reach the low to mid-90s for the first time. By June 28th, Portland's temperature climbed to 116 degrees Fahrenheit, 46.7 degrees Celsius, obliterating the city's previous all-time record by a margin that in climate terms is almost unheard of. Normally, when a daily or all-time temperature record falls, it falls by a degree, maybe 2. Portland's record fell by multiple degrees in a single day. Salem, Oregon, reached 117 Fahrenheit. Seattle topped out at 108. And just across the border in British Columbia, the small town of Lytton, population around 250, with another 1,500 to 2,000 First Nations residents living on nearby reserves, began climbing toward numbers that no one in Canadian history had ever recorded. On June 27th, Lytton hit 46.6 degrees Celsius, breaking the Canadian national record. The next day, June 28th, it broke that record again, reaching 47.9, and on June 29th it broke it a third time, 49.6 degrees Celsius, 121.3 Fahrenheit. 3 consecutive days, 3 consecutive national records. in a town that, under normal circumstances, might see a summer high in the low 30s Celsius. The temperature anomaly in Lytton wasn't a few degrees above normal, it was somewhere around 20 degrees Celsius above what the region typically experiences in late June. 20 degrees. Try to sit with that for a second. Imagine whatever the normal high temperature is where you live on a comfortable summer day, and then imagine it spiking 20 degrees Celsius. That's 36 degrees Fahrenheit. Above that in the span of a single weather event. And then on June 30th, the day after Lytton set its third consecutive national heat record, a wildfire ignited just south of the town. Within a matter of hours, it tore through Lytton itself. The fire destroyed most of the town's buildings, forced the evacuation of more than 1,000 residents, and tragically killed 2 civilians. The cause was never officially determined, though human activity was considered the likely trigger, possibly something as mundane as a spark from a passing train in tinder-dry conditions created by days of unprecedented heat. The fire burned through more than 83,000 hectares, that's over 300 square miles, before it was brought under control. A town that had 3 days earlier made international headlines for setting a national heat record was now largely gone. While Lytton was burning, the human toll across the broader region was mounting in a way that took weeks to fully tabulate. The British Columbia Coroner's Office eventually confirmed 619 heat-related deaths during the most intense period of the heatwave alone, June 25th through July 12th. In Oregon and Washington, medical examiners were simultaneously investigating dozens, then hundreds, of possible heat-related deaths. By the time researchers pulled together the full picture, estimates for the broader region ranged widely depending on methodology. Somewhere around 800 confirmed excess deaths across British Columbia, Washington, and Oregon combined when using stricter confirmation criteria, with some broader statistical estimates of total excess mortality running as high as 1,400. Either way you slice it, this was by a wide margin the deadliest weather event in the recorded history of the Pacific Northwest. Why so deadly? This is the part that matters most for understanding the danger, because it isn't really about the absolute temperature. It's about the combination of 3 things: high temperatures, a population that is physiologically unacclimated to that kind of heat, and a built environment that for the most part had never needed to handle it. Let's take those one at a time. First, acclimation. Human bodies adapt to heat over time through a process that takes roughly 1 to 2 weeks of repeated exposure, increased sweating efficiency, changes in blood plasma volume, adjustments in how the body manages its core temperature. Someone living in, say, Phoenix, Arizona, where summer highs regularly exceed 110 degrees Fahrenheit, has a body that has adapted to that reality, season after season, year after year. A resident of Seattle or Portland, where the average warmest day of the year sits in the low to mid-90s, simply does not have that same baseline adaptation. When the temperature jumps not just above normal, but 20 to 30 degrees above what the body is used to, the margin for error collapses. Heat exhaustion, then heat stroke, can develop faster and with less warning in an unacclimated body. Second, infrastructure. Air conditioning penetration in the Pacific Northwest prior to 2021 was estimated at somewhere around 40 to 50% of households in many parts of western Washington and Oregon. And that's being generous for some neighborhoods. Compare that to the American Southwest or the Southeast, where air conditioning penetration approaches universal coverage, often above 90%. During the 2021 event, cooling centers were opened across Portland, Seattle, and Vancouver, but demand outstripped capacity in many locations, and, critically, many of the people most at risk were elderly residents living alone, in upper-floor apartments without air conditioning, who either couldn't easily travel to a cooling center or didn't recognize the danger they were in until it was too late. Heat doesn't announce itself the way a flood or a fire does. There's no ESSA, there's no visible threat, just a slow, cumulative physiological strain that, for someone in a vulnerable health category, can become lethal over the course of a single afternoon and evening without dramatic external signs. Third, and this is the piece that connects directly to this week's forecast, overnight low temperatures. This is, according to public health researchers, one of the most underappreciated factors in heat mortality. A single hot day, even an extremely hot day, is survivable for most people if the body gets a chance to recover overnight. But when overnight lows stay elevated, when temperatures that should drop into the 60s Fahrenheit instead only fall into the 70s, or even stay in the 80s, the body never gets that recovery window. Heat stress becomes cumulative day over day, and that's when mortality risk climbs sharply. During the 2021 event, overnight lows in parts of the region stayed unusually warm for several consecutive nights, denying that critical recovery period to people who are already struggling. Let's pause here and actually go inside the body for a moment, because understanding what heat stroke physically is, not just as a scary phrase on a warning label, but as a measurable physiological process, makes everything we've just discussed, and everything still to come, click into place in a way that a list of temperatures alone never quite does. Your body, under normal conditions, sits at a core temperature close to 37 degrees Celsius, about 98.6 Fahrenheit, and it defends that temperature fiercely because the proteins and enzymes that make every cell in your body function are calibrated to operate within a very narrow range around that number. When you're in a hot environment, your body's primary defense is sweat. As sweat evaporates off your skin, it carries heat away with it. That's evaporative cooling, the same physical process that makes a wet towel feel cold when you wave it through the air. This system works extraordinarily well, right up until it doesn't. And the thing that breaks it isn't just temperature, it's humidity. This is where a measurement called wet bulb temperature comes in. And it's one of those concepts that once you understand it, you'll start noticing referenced in heat coverage everywhere. A standard thermometer, what scientists call a dry bulb thermometer, just measures the air temperature. A wet bulb thermometer is wrapped in a damp cloth, and as air passes over it, water evaporates from that cloth, cooling the thermometer below the actual air temperature by an amount that depends on how much moisture the air can still absorb. In very dry air, that evaporation happens easily, and the wet bulb reading can be dramatically lower than the dry bulb reading. In very humid air, air that's already close to saturated with moisture, evaporation barely happens at all, and the wet bulb reading sits close to the actual air temperature. Your sweat works exactly like that wet cloth. And the wet bulb temperature, essentially, tells you how effectively your sweat can cool you down, regardless of how hot the air itself actually is. For more than a decade, the scientific consensus, based on an influential 2010 paper by researchers Sherwood and Huber, held that a wet bulb temperature of 35 degrees Celsius, about 95 Fahrenheit, represented an absolute upper limit for human survival, the point beyond which a healthy person, even at rest in the shade with unlimited water, could not survive more than about 6 hours, because the body would simply have no physical mechanism left to shed heat. Above that wet bulb threshold, core temperature climbs steadily and uncontrollably toward the roughly 40 to 43 degrees Celsius range, where heat exhaustion gives way to heat stroke and, eventually, organ failure. But, and this is where the science has moved fast in just the last couple of years, newer research, including controlled human subject studies published through 2025 and into early 2026, has found that this 35-degree wet bulb threshold was actually too generous. Real human bodies, tested in climate chambers under carefully controlled conditions, started losing the ability to thermoregulate, meaning their core temperature began rising even at rest at wet bulb temperatures considerably lower than 35 degrees Celsius. Some of this research has found thresholds as low as roughly 31 to 32 degrees Celsius wet bulb for young, healthy adults under certain conditions, with even lower thresholds for older adults. In some analyses, 6 to 13 degrees Celsius lower than the old 35-degree benchmark, depending on whether conditions are hot and dry versus hot and humid. One newer physiological model, published in Nature Communications in early 2026, found that non-survivable conditions, based on a more detailed whole-body heat exchange calculation rather than the older simplified threshold, have already occurred during several real historical heat events, all of them below that old 35-degree wet bulb benchmark, and with regular exceedances of deadly thresholds specifically for older people exposed directly to the sun. So why does any of this matter for a forecast of 98 degrees Fahrenheit in Portland, which, in dry bulb terms, is nowhere near that 35 degrees Celsius, 95 Fahrenheit wet bulb danger zone? 2 reasons. First, because it reframes what a dangerous temperature actually means. It's never just the number on the thermometer, it's that number combined with humidity, combined with sun exposure, combined with how long someone is exposed, combined with their age and health status, and access to a cooler space to recover in. The Pacific Northwest heat events tend to be relatively dry heat events, which sounds like it should be safer, and in pure wet bulb terms, it often is compared to an equally hot but humid event somewhere like the southeastern United States, or, for that matter, somewhere in Southeast Asia during the hot season. But relatively safer in wet bulb terms doesn't mean safe. It just means the dominant risk factor shifts from the body's cooling system being physically overwhelmed by humidity toward the body's cooling system being overwhelmed by sheer duration and lack of recovery time, which is exactly the overnight low mechanism we just spent so much time on. Second, and this is the broader point this channel keeps coming back to, These physiological thresholds aren't static numbers sitting in a textbook somewhere. They're an active area of research, being revised downward as better data comes in, which mirrors almost exactly what we discussed earlier about the Cascadia subduction zone, a system that scientists thought they understood reasonably well, until new instrumentation and new methods revealed it was more complicated, and in some ways more concerning than the older models suggested. Heat physiology is going through the same process right now. The threshold that was treated as a hard physical limit for over a decade is being replaced by a more nuanced, more conservative, and frankly more alarming picture, one where the margin between uncomfortable and dangerous is narrower than previously believed for everyone, but especially for older adults, for whom some of this newer research suggests survivable thresholds that are dramatically lower than the population-wide average. Now, here's where this connects directly back to the bulletin we opened this video with. Remember the Portland Extreme Heat Watch issued June 9th? Buried in the additional details of that bulletin is a line specifically about overnight temperatures. Forecasters note that low temperatures between 63 and 66 degrees Fahrenheit are possible for Monday and Tuesday mornings, June 15th and 16th. That sounds, on its face, like reasonable relief. Mid-60s overnight is not dangerous on its own, but the bulletin goes further, and this is the line that should catch your attention if you're paying close attention to how these forecasts are written. There is a 10 to 20% chance that overnight low temperatures remain above 70 degrees Fahrenheit, which would lead to what the bulletin calls limited overnight relief, a 10 to 20% chance. That's not the headline number, that's the tail risk, the scenario buried in the percentages that, if it happens, starts to nudge this event from uncomfortable toward genuinely dangerous, especially for anyone in an upper-floor apartment without air conditioning, especially for the elderly, especially for outdoor workers who might be putting in long days during the hottest hours, and then going home to a space that never properly cools down. This is exactly the kind of detail that separates a casual heat wave from a heat event with real public health stakes, and it's also exactly the kind of detail that almost never makes it into a casual conversation about "it's going to be hot this weekend." The headline highs, 95 to 100 degrees Fahrenheit, are the number everyone will see on their phone's weather app, but the overnight lows, and whether that recovery window exists, are arguably more important for predicting whether this event causes real harm. So where does that leave us, as of this recording, with the forecast for the days immediately ahead? Let's pull up the most recent numbers we have for Portland specifically, because the 7-day forecast for the Portland forecast point coordinates roughly 45.53 degrees north, 122.67 degrees west, gives us a granular, day-by-day look at exactly how this is expected to unfold. According to the National Weather Service forecast for that point, the build-up looks gradual rather than sudden. Friday, the day before the bulk of the heat arrives, is forecast as sunny with a high near 78 degrees Fahrenheit and an overnight low around 53, comfortable, almost cool by summer standards. Saturday continues that gentle climb, sunny with a high near 80, an overnight low around 55, with north-northwest winds gusting as high as 18 miles per hour. Then comes the jump. Sunday, the forecast shows a high near 92 degrees Fahrenheit with northeast winds, and that wind direction matters, because northeast and east winds in this region often signal offshore flow, the pattern where air moving from the interior toward the coast brings drier, hotter conditions, sometimes pushing coastal areas to be even warmer than the cities themselves. The overnight low Sunday into Monday sits around 62, and then Monday and Tuesday, June 15th and 16th, the heart of the extreme heat watch, both show highs near 98 degrees Fahrenheit, with overnight lows hovering around 65. 98 degrees 2 days in a row, with low overnight relief in the mid-60s under the base forecast, but with that 10 to 20% tail risk of staying above 70. Now 98 is not 116. Let's be very clear about that. The forecast, as it stands right now, is not calling for anything close to the all-time record set in 2021, but 98 degrees for 2 consecutive days, in a region where the population skews toward limited air conditioning and limited heat acclimation, sitting on top of an extreme heat watch that explicitly invokes the language of dangerous conditions. That's not nothing either. And it's worth remembering that the 2021 event didn't arrive as a single freak day. It built over several days, each one hotter than the last, with the body's cumulative stress compounding as the week wore on. If this week's pattern behaves the way the current models suggest, a build-up through the weekend, peaking Monday and Tuesday, the shape of the curve, even if the peak number is lower, rhymes with 2021's shape, just at a lower amplitude. For now, and that "for now" is doing a lot of work in this story, because there's a wider context here that the day-to-day forecast doesn't capture on its own. This isn't an isolated hot weekend appearing out of nowhere in an otherwise normal spring. This heat wave is arriving at the tail end of a season that has already been unusually warm and unusually dry across much of the western United States. And understanding that broader pattern is going to help us answer the bigger question this video is built around. So let's zoom out and look at what the spring of 2026 has looked like across the American West more broadly, because the answer might surprise you. Go back to mid-March of this year. NOAA's Climate Prediction Center put out a spring outlook that frankly read like a preview of what's happening right now. As of mid-March, roughly 55% of the continental United States was experiencing moderate to exceptional drought, following a winter that had been warmer and drier than average across huge swaths of the country. John Gottschalk, who leads the Operational Prediction Branch at NOAA's Climate Prediction Center, said at the time that drought conditions had worsened or developed across much of the Great Plains, the lower Mississippi Valley, and the Southeast, all because of that warmer, drier winter, and forecasters specifically called out the Pacific Northwest, the Great Basin, the Central Rockies, the Southwest, and the South Central Plains as the regions most likely to see those conditions worsen or spread through the spring. Then, in mid-March itself, the West got an early taste of what was coming. A heat dome, yes, already in March, settled over the Southwest, with the National Weather Service forecasting 114 degrees Fahrenheit near the Salton Sea in California. If that number had held, it would have broken the national record for March by 6 degrees Fahrenheit, and surpassed the existing April record of 113 degrees. One widely shared meteorological commentary at the time called it potentially the most extraordinary heat wave in the United States since the 2021 Pacific Northwest event, though notably, that March 2026 heat wave was centered over the desert Southwest, a region that, unlike the Pacific Northwest, is at least somewhat built for extreme heat. Climate researchers later compared the March 2026 event to a similar anomalous warm spell that hit the Midwest and Northeast back in March of 2012, noting that thousands of daily records and hundreds of monthly records fell in both cases. The difference, as one Yale Climate Connections analysis put it, was that the March 2026 event hit a part of the country that's naturally warmer to begin with, so instead of producing shocking 80-degree readings in places like Michigan, it produced shocking 100-plus degree readings across the desert Southwest, weeks earlier in the year than anyone expected. By late March, when NOAA released its full spring outlook for April through June, the pattern was set. The Climate Prediction Center's outlook favored above normal temperatures for most of the contiguous United States, with the highest probabilities, greater than 60%, concentrated specifically over the Central Great Basin, the Rockies, and parts of the Southwest. On the precipitation side, the outlook called for below-normal seasonal precipitation across the Pacific Northwest, much of the Intermountain West, the Rockies, and the Central High Plains and Great Plains. In other words, and this is the through line you need to hold on to, the entire spring of 2026 has been trending warmer and drier than normal across almost the entire western United States, well before this week's heat dome ever showed up on a forecast model. This isn't a heat wave that materialized out of a calm average spring. It's the latest entry in a season that's been running hot since at least March. And as we head into June, the Washington State Climate Office's most recent outlook, published in mid-May, continued to show above normal temperatures likely statewide for the month of June, with expectations for warmer and drier conditions continuing across Washington more broadly. Now, does a warm, dry spring guarantee a dangerous summer heat dome? No. Plenty of warm, dry springs pass without producing anything close to a 2021-style event. But a warm, dry spring does set the stage in a few specific ways that matter for what comes next. Dry soil heats up faster and more efficiently than moist soil because there's less moisture available to absorb energy through evaporation, so the ground itself becomes a more effective amplifier of any heat dome that does form on top of it. Low snowpack in the mountains means less of that natural air conditioning effect that meltwater normally provides to nearby valleys through the early summer. And widespread drought conditions mean that when a heat dome does arrive, the vegetation underneath it is already primed, drier, more stressed, more flammable, which is exactly the kind of setup that turned the aftermath of the 2021 heat dome into one of the most significant wildfire seasons in recent North American history. One peer-reviewed analysis found that the 2021 heat dome alone accounted for somewhere between 21 and 34% of the total area burned by wildfire across North America that entire year. So when this week's extreme heat watch arrived, It didn't arrive in a vacuum. It arrived on top of a spring that NOAA had been flagging as anomalously warm and dry since mid-March. The red flag warnings already posted for parts of the region this week, for wind gusts up to 30 miles per hour combined with low humidity, creating conditions where any new wildfire ignition could spread rapidly, aren't a coincidence. They're a direct consequence of that broader seasonal trend meeting this week's heat. And while we're on the subject of the broader regional picture, here's something that might seem completely unrelated at first, but that I think is worth including, because it's a perfect example of how the Pacific Northwest's weather this spring has been swinging between extremes in a way that's almost disorienting. On the very same day, June 9th, 2026, that the National Weather Service Portland office issued that extreme heat watch for the days ahead, the National Weather Service office in Spokane, on the other side of the Cascade Mountains, issued a flood warning, not a heat advisory, a flood warning, for the Stehekin River affecting Chelan County, with minor flooding forecast and water levels reported at 20.3 feet against a bankful stage of 19, 5 feet, close enough that the bulletin specifically warned about water beginning to damage roads and culverts in the area. And on that same day in Medford, Oregon, in the southern part of the state, the National Weather Service issued a frost advisory, warning that temperatures between 33 and 36 degrees Fahrenheit would produce frost. Read that again, on the same day, a heat watch warning of dangerous 95 to 100 degree conditions in Portland, a flood warning from snowmelt-driven river rises in north-central Washington, and a frost advisory in southern Oregon, all three issued by National Weather Service offices on June 9, 2026. This is what a region in seasonal transition looks like when the transition itself becomes more volatile. It's not that any single one of these bulletins is unprecedented on its own. Frost in early June in higher elevation parts of southern Oregon isn't shocking, and minor river flooding from snowmelt happens most years in north-central Washington. But the simultaneous presence of all three, frost, flood, and extreme heat warnings, issued by the same regional weather service network on the same calendar day, captures something that climate researchers have been documenting for years now. The term that's become common in meteorological circles is weather whiplash. Rapid swings between extremes compressed into shorter timeframes, layered on top of each other in ways that strain the systems, both natural and human, that are built around more gradual, predictable seasonal transitions. Okay, so we've built the picture. We understand what a heat dome is mechanically. We've walked through 2021 in detail, the human toll, the Lytton wildfire, the acclimation and infrastructure factors that turned a weather event into a mass casualty event. We've established that this week's heat wave is arriving on top of an already anomalous spring, and we've looked at the actual numbers for the days ahead, a build-up through the weekend, peaking around 98 degrees Fahrenheit on Monday and Tuesday, June 15th and 16th, with overnight lows hovering in the mid-60s under the base forecast but carrying a 10 to 20% chance of staying above 70. Now I want to take you somewhere that might feel like a left turn, but I promise it connects. Because if you're a regular viewer of this channel, you know that we don't just cover weather. We cover earthquakes, volcanic activity, space weather, and yes, occasionally, the fringe ideas that circulate around all of these topics. And there's a question that comes up again and again in comment sections whenever the Pacific Northwest gets mentioned in any context at all. The question is this: does extreme weather, specifically extreme heat, have any connection to the Cascadia subduction zone? Could a heat dome in any way be linked to the big one that this region has been bracing for decades? Let's address this head on, because the honest answer requires us to first understand what the Cascadia subduction zone actually is, what the latest research says about it, research that's been published just in the past few months. And then to clearly separate the science from the speculation, the Cascadia subduction zone is a roughly 1,100 to 1,300 kilometer long fault running from northern California up through Oregon and Washington, and into Vancouver Island in British Columbia. It marks the boundary where the Juan de Fuca and Gorda oceanic plates are being forced underneath the North American continental plate, a process called subduction. Right now, this fault is largely locked. The plates are stuck together by friction, slowly building up strain, the same way you'd build up tension in a rubber band by stretching it further and further. The last time this fault ruptured catastrophically was January 26th, 1700. We know the exact date because the tsunami it generated was recorded by observers across the Pacific in Japan, even though nobody in the Pacific Northwest at the time had a written record-keeping system that survived. Based on that history, Researchers estimate there's roughly a 10 to 15% chance of a full-length rupture producing a magnitude 9 or greater earthquake within the next 50 years. Separately, there's an 85% chance of a magnitude 6, 5 or greater deep earthquake in the Puget Sound region within a similar time frame, and a 17% chance of a magnitude 6.5 or greater shallow crustal earthquake. These are different fault types within the broader Pacific Northwest hazard picture, not all the same fault. Now, here's where it gets interesting from a pure research standpoint, completely separate from any heat-related discussion. Earlier this year, February 2026, researchers published a study in the journal Science Advances, led by a researcher named Malin Kidiwela, examining seismic noise data to map fluid pathways and what they called active protothrusts within the Cascadia subduction zone. The findings suggested that while the northern segment of the fault remains locked in the way scientists have long understood, the central region shows evidence of slow slip events and fluid movement, patterns that suggest a kind of partial unlocking, at least in terms of how fluids move through the fault system. The study found that other faults running perpendicular to the main subduction zone may act as pathways that let trapped fluid escape, and one of the researchers noted that during a megathrust rupture, fluid pressure is one of the ways an earthquake propagates, so a fault system with more pathways for fluid release could behave differently during a large earthquake than a fault system without them. Then, in April 2026, a separate piece of reporting highlighted another recent discovery. Seismic imaging off Vancouver Island had revealed what researchers described as a tear in the subducting oceanic plate beneath the Cascadia subduction zone. For a brief moment, this generated some public excitement, with headlines suggesting Cascadia might be shutting down, potentially good news, in the sense of reduced earthquake risk, for the millions of people living across this hazard zone. But the researchers were quick to clarify that this is far more complicated than a simple shutdown. The tear appears to be localized to part of the zone near Vancouver Island, and the broader Cascadia subduction zone remains an active subduction system fully capable of producing the kind of large earthquake the region has been preparing for. Rather than signaling an end to the hazard, the discovery highlighted just how much remains uncertain about the detailed structure and behavior of this fault system, uncertainty that researchers are actively working to reduce through projects like the Underwater Observatory, that the University of Washington received over $10 million to build back in 2023, specifically to monitor this stretch of seafloor in far greater detail than has ever been possible before. To be crystal clear, none of this research has anything to do with heat domes. These are seismic studies examining the physical structure and fluid dynamics of a tectonic plate boundary that operates on timescales of centuries, using data collection methods, seismic noise analysis, seafloor imaging, that are completely independent of surface weather conditions. But here's where the fringe theory comes in, because it inevitably does, and our job on this channel is never to pretend these ideas don't exist. Our job is to name them, examine them honestly, and tell you clearly where they stand relative to mainstream science. There is a long-running idea, popular in certain corners of the internet, that extreme weather events, heat waves, sudden pressure changes, even geomagnetic storms can act as a kind of trigger for seismic activity, nudging an already stressed fault past some tipping point it was approaching anyway. The reasoning usually goes something like this. A massive heat dome represents an enormous, sustained high-pressure system sitting over a region for days. Barometric pressure changes do exert a measurable, if tiny, force on the Earth's crust, and therefore, the thinking goes, a large enough pressure anomaly could theoretically influence the timing of an earthquake on a fault that's already close to failure. This isn't accepted by mainstream science. Let's be very precise about why. Researchers have in fact studied the relationship between atmospheric pressure changes and seismicity, and there is some evidence in certain very specific tectonic settings for extremely subtle correlations between large barometric pressure swings and very small earthquakes, sometimes called micro-triggering. But the effect, where it has been observed at all, is tiny. We're talking about pressure changes on the order of a few hectopascals influencing stress on a fault by an amount that's a vanishingly small fraction of the stress already stored in a fault like Cascadia, which has been accumulating strain for over 300 years. The idea that a heat dome, even an extraordinarily powerful one, could meaningfully influence the timing of a magnitude 9 megathrust rupture that's been building for centuries is not supported by any peer-reviewed seismological research. Take it as a thought to sit with, not a conclusion. It's the kind of pattern-seeking that's deeply human. We see two dramatic things happening in the same region around the same time, and our brains want to connect them. But wanting a connection to exist, and that connection being real, are two very different things. What is real, and what mainstream seismologists do take seriously, is something almost the opposite of dramatic. It's the ongoing, decades-long effort to better understand a fault system that remains, in their own words, unusually quiet for a megathrust. The Cascadia subduction zone doesn't produce the regular small to moderate earthquakes that most other subduction zones around the world do, which is part of why it's so hard to study, and part of why every new piece of research, like the fluid pathway study from February or the plate tear discovery from April, gets so much attention. Scientists aren't bored. They're working with an unusually data-poor fault that happens to sit underneath several million people, and it's worth being specific about what unusually quiet actually means in practice, because it connects to something we touched on briefly earlier. While the Cascadia megathrust itself stays largely silent, the broader region around it is not silent at all. Earlier this year, a swarm of roughly 18 small earthquakes was recorded off the Washington coast over the course of a weekend, with the strongest reaching magnitude 4.2, located around 240 miles west of the coastal town of Westport. According to the director of the Pacific Northwest Seismic Network, these quakes occurred along the Juan de Fuca Ridge, not the subduction zone itself, but the spreading center where the Juan de Fuca plate is being created, pulling apart from the neighboring Pacific plate. It's a different process entirely from subduction, but it's a useful reminder that the Pacific Northwest sits at the intersection of multiple active tectonic processes, even though the one that gets the most attention, the big one on the Cascadia megathrust, remains the quiet one. This is also where the region's earthquake preparedness culture comes in, and it's worth mentioning because it runs on a parallel track to the heat preparedness culture we've spent most of this video discussing. Both are responses to low frequency, high consequence events, and both rely on the same basic principle, which is that preparation has to happen during the quiet periods, because there's no reliable way to know when the quiet period will end. Washington and Oregon both participate in an annual event called the Great Shakeout, an earthquake drill where people practice the basic protective action recommended during shaking. Drop, cover, and hold on, meaning drop to the ground, take cover under something sturdy, and hold on until the shaking stops. In a recent year, roughly 1.5 million people in Washington alone participated. Washington ranks as the second most earthquake-threatened state in the lower 48, behind only California, with Oregon ranking third, a ranking that surprises a lot of people who associate major US earthquake risk almost exclusively with California. The parallel to this week's heat story is almost exact. Just as the region has spent the years since 2021 building out heat preparedness infrastructure, cooling centers, extreme heat watches issued days in advance, public messaging about overnight lows and vulnerable populations, it has spent decades building out earthquake preparedness infrastructure, even though, statistically, most people living through that preparation will never personally experience the magnitude 9 event the preparation is ultimately aimed at. The 10 to 15% 50-year probability we mentioned earlier means that, for any individual, the much more likely outcome is living an entire lifetime without experiencing the full Cascadia rupture, but the consequences of that rupture, if and when it happens, are severe enough that the preparation makes sense anyway, the same logic that applies to having a fire extinguisher in your kitchen, even though most likely you'll never need it. If you want one practical takeaway from this section, separate from anything about this week's heat forecast, it's this. If you live in the Pacific Northwest, or if you're watching this and you live anywhere with a known major earthquake hazard, the standard guidance is the same regardless of which specific fault is the concern. Know how to drop, cover, and hold on. Have a basic emergency kit, water, non-perishable food, a flashlight, a way to charge your phone, sufficient for at least a few days, since infrastructure recovery after a major earthquake, especially one with an associated tsunami along the coast, can take considerably longer than a few days in the hardest hit areas. And if you live near the coast in the Cascadia hazard zone specifically, know your tsunami evacuation route in advance, because unlike most of the heat-related guidance we've discussed tonight, which gives you hours or days of warning, a Cascadia tsunami could arrive within minutes of the shaking itself. There may be no time to look up a map once it starts. Alright, let's bring this back to the here and now, and to the question this whole video is built around. We've covered the mechanics of heat domes, the human cost of 2021, the broader anomalous spring of 2026, and we've addressed the Cascadia question honestly. Now let's talk about what this all means practically, for the power grid, for daily life, for anyone in the Pacific Northwest right now, and for our viewers watching from much farther away, including here in Vietnam, where the connection might not be obvious at first glance, but is more real than you might think. Start with the power grid, because this is one of those places where heat domes create cascading effects that most people never think about until the lights actually go out. When temperatures spike across a region the way they're forecast to this weekend, electricity demand spikes right alongside them, almost entirely driven by air conditioning load. And remember, in the Pacific Northwest, that's a smaller percentage of households than in most of the country, but it's a percentage that has been growing fast since 2021, precisely because of events like this one. People who went through 2021 without air conditioning bought window units afterward. Multiply that across a region, and you get a grid that's now carrying more cooling load during heat events than it used to, even before you account for the broader trend of rising electricity demand from data centers and other large industrial users. This isn't unique to the Pacific Northwest. Look at what's happening this summer across the broader Western grid. The Electric Reliability Council of Texas, ERCOT, which manages around 90% of that state's power for roughly 27 million customers, released its summer 2026 outlook warning that peak demand could exceed 92.2 gigawatts, which would be a new all-time record, surpassing the previous record of 5 gigawatts set in August 2023. ERCOT's own assessment puts the odds of an actual grid emergency at around 0.9% for June and 0.21% for July. Low numbers but not zero, and notably, ERCOT specifically said it cannot rule out a repeat of summer 2023, which was the second hottest summer on record for the state, particularly if the wetter spring pattern Texas has seen fades early in June. Further east, the grid operator PJM, which covers a huge swath of the Mid-Atlantic and Midwest, saw demand exceed 161 gigawatts during a June 2025 heatwave, the third highest in that operator's history, and had to deploy demand response programs, essentially paying large users to reduce consumption during peak hours to avoid more serious measures. The point here isn't that the Pacific Northwest grid is about to fail this weekend. There's no indication of that, and the forecast highs of around 98 degrees Fahrenheit, while serious from a public health standpoint, are well within what regional utilities plan for. The point is that this is the broader backdrop. Grids across the western United States are operating closer to their margins during heat events than they used to. The margins are getting tested earlier in the season, and more frequently, and a region like the Pacific Northwest, which historically built its grid around winter heating demand, not summer cooling demand, is in the middle of an infrastructure adjustment that 2021 kicked into high gear and that events like this week's heatwave continue to reinforce. Now, let's bring in one more thread, because this channel covers space weather too, and there's a reason we do. Even when the connection to a story like this one is more about parallel timing than direct causation. As of the NOAA Space Weather Prediction Center's most recent 3-day forecasts from early June, the geomagnetic environment has been notably active. The forecast issued June 8th at 12:30 unit ECT noted that the greatest expected 3-hour KP index for the June 8th through 10th window reached 667, corresponding to G3, a strong geomagnetic storm on NOAA's 5-level scale which runs from G1 minor up to G5 extreme. The rationale cited was the anticipated passage of a coronal mass ejection. That's a coronal mass ejection, essentially a continent-sized cloud of charged particles thrown off the Sun at speeds that can exceed 1,000,000 miles an hour, that had left the Sun on June 6th. And just a few days before that, the forecast issued June 5th flagged periods of G1 to G3 storming, with a chance of G4 severe storm periods, tied to multiple CMEs that left the Sun on June 3rd. So why mention this in a video about a heat dome? Not because there's any established physical link between geomagnetic storms and surface weather. There isn't, and we want to be clear about that. This isn't the fringe theory section of the video. We're mentioning it because of the grid angle. Geomagnetic storms, particularly G3 and above, can induce currents in long power transmission lines, a phenomenon called geomagnetically induced current, which utilities have to monitor and sometimes actively manage by adjusting transformer loading, or, in extreme cases, taking certain lines offline temporarily. When a grid is already under elevated stress from heat-driven demand, having a geomagnetic storm in the same general window adds another variable that grid operators have to track, even if the two phenomena are completely unrelated in their origins. It's less these things are connected, and more this is what it looks like when multiple independent stressors land in the same calendar week, which again ties back to that broader weather whiplash idea we mentioned earlier, just extended from the atmosphere all the way up into the magnetosphere. To put this June's G1 to G3 activity in perspective, it's worth remembering what a truly extreme version of this looks like, because we covered it in depth on this channel when it happened. Back in May of 2024, a solar active region designated AR3664 produced a sequence of X-class flares. X-class being the most powerful category on the scale used to measure solar flare intensity, with each letter category from A through B, C, M and X representing roughly a tenfold increase in X-ray output, and launched a series of coronal mass ejections toward Earth over the course of about a week. The result was a G5 extreme geomagnetic storm, the highest level on NOAA's scale, with a KP index that reached 9, the maximum possible reading, and a DST index, a separate measure of how disturbed Earth's magnetic field becomes during a storm, that dropped to negative 412 nanotesla. For context on how extreme that is, the storm we just discussed from early June 2026 was forecast to reach a maximum 3-hour KP of 667, corresponding to G3. The May 2024 event reached KP 9, a full 2.5 steps higher on a scale that isn't linear. Each step up represents a substantially larger disturbance to Earth's magnetic field, and the geomagnetically induced currents that utilities have to manage scale up correspondingly. That May 2024 storm was at the time described as the most intense geomagnetic storm since the famous Halloween storms of October 2003, more than 2 decades earlier, and it produced aurora visible as far south as Mexico and parts of the Mediterranean, locations that essentially never see the northern lights under normal conditions. We bring this up not to suggest that this June's G1 to G3 activity is anything close to that scale. It isn't by a wide margin. We bring it up because it illustrates the range of what geomagnetic storm can mean, and why the specific G level matters so much when you're assessing grid risk. A G1 storm is, for most practical purposes, a non-event for the power grid. It might produce some aurora at high latitudes, and that's about it. A G3 storm, like the one forecast for early June 2026, starts to require more active monitoring from grid operators in higher latitude regions, though it's still well within the range that modern grid management handles routinely. A G4 or G5 storm, like May 2024, is the kind of event where utilities actively reconfigure parts of the grid, where satellite operators may delay maneuvers, where high-frequency radio communications, used by aviation, by some maritime operations and by amateur radio operators, can experience significant degradation or complete blackouts on the sunlit side of the planet for periods of time, and where the kind of geomagnetically induced currents we mentioned can, in extreme historical cases, most famously the 1989 Quebec blackout, triggered by a geomagnetic storm that knocked out power to millions of people for around 9 hours, actually cause grid failures, not just stress on an already strained system. This is also a good moment to address something that comes up constantly in comment sections whenever this channel covers space weather alongside other Earth phenomena: the question of whether solar activity itself follows any kind of predictable long-term cycle that might help anticipate periods of elevated risk. And the answer is yes, in a general sense. The Sun follows an approximately 11-year cycle of rising and falling activity, called the solar cycle, with activity peaking around what's called solar maximum and reaching its quietest point at solar minimum. The current cycle, solar cycle 25, has been running notably more active than many forecasters predicted several years ago, with solar maximum generally considered to have occurred sometime around late 2024 into 2025, which is part of why events like the May 2024 G5 storm happened when they did, and why we've continued to see elevated geomagnetic activity, including the G1 to G3 periods in early June 2026, even as the cycle moves past its peak. Solar cycles don't switch off abruptly at maximum. Activity tends to remain elevated for a year or more afterward, with the decline towards solar minimum happening gradually over the following several years. So when you see this channel covering G1 to G3 storm forecasts in mid-2026, that's broadly consistent with where we'd expect to be in the solar cycle, elevated, but past the most extreme peak. None of this changes the forecast for Portland this weekend. The heat dome and the geomagnetic storm are, as we said, independent phenomena with no causal link between them. But understanding both of them, and understanding roughly where each one sits on its own scale of severity, a G3 storm that's notable but manageable, a heat wave that's serious but so far, short of 2021's historic signature, is part of what this channel tries to do every time we cover a week like this one. Not to inflate every story to maximum drama, and not to dismiss every story as routine, but to give you the actual scale, so you can calibrate your own sense of concern accordingly. Now, Vietnam. If you're watching this from Ho Chi Minh City, from Hanoi, from anywhere in Southeast Asia, you might reasonably be wondering what any of this has to do with you. The Pacific Northwest is thousands of kilometers away, on the opposite side of an ocean, in a completely different climate zone. Fair point. But here's the connection, and it's worth understanding because it'll help you make sense of weather patterns closer to home too. The same broad atmospheric circulation patterns that influence whether a ridge sets up over the Pacific Northwest are connected to the larger Pacific-wide circulation that also governs phenomena like El Niño and La Niña, the cyclical warming and cooling of sea surface temperatures across the central and eastern Pacific that has ripple effects on weather patterns across the entire Pacific basin, including monsoon timing and intensity across Southeast Asia. As of earlier this year, the Washington State Climate Office's outlook noted that La Niña conditions had been in place, but that a return to neutral conditions was expected by March 2026. That transition, from La Niña toward neutral and potentially toward El Niño later in the year, matters enormously for Vietnam, because El Niño years have historically been associated with delayed monsoon onset and reduced rainfall across much of Vietnam, particularly affecting the Mekong Delta and Central Highlands, while La Niña years tend to bring wetter conditions and an increased risk of tropical cyclone activity in the South China Sea. So while a heat dome over Portland and a monsoon delay over the Mekong Delta might seem like two completely separate stories, they're both downstream effects of the same broader Pacific Ocean atmosphere system shifting its configuration. When you hear about an El Niño or La Niña transition in a Pacific Northwest weather report, that's not just American news. It's a signal about the broader system that, with a lag of weeks to months, also shapes whether your wet season starts on time, whether it's wetter or drier than normal, and whether tropical cyclone activity is more or less likely in the months ahead. We'll be tracking this transition on this channel as it develops through the rest of 2026, because the implications for Vietnam's agricultural calendar, particularly rice cultivation timing in the Mekong Delta, which is acutely sensitive to monsoon onset timing, are significant. And here's something worth sitting with for a moment, because it puts everything we've discussed about the Pacific Northwest into a slightly different light. While Portland and Seattle are bracing for highs near 98 degrees Fahrenheit, about 37 degrees Celsius, and treating that as a genuinely dangerous, watch-worthy event, Vietnam has, just in the past few weeks, already been through heat that's considerably more extreme by raw numbers. Go back to late May. On May 25th, Hanoi's Lang monitoring station recorded 40.7 degrees Celsius. Phu Tho province, just northwest of the capital, topped the entire country that day at 40.8 degrees. Several other stations across northern Vietnam, Bac Ninh at 40.5, Hoi Xuan in Hanoi at 40.5, Do Luong in Nghệ An at 40.3, Hoang Kia in Ha Tinh at 42, all crossed the 40-degree threshold on the same day. Vietnam's National Center for Hydrometeorological Forecasting described this as the second major heat wave of May 2026, more intense and longer lasting than an earlier event in mid-May, and ranked it among the three most severe May heat waves the country has recorded since 2021. Forecasters attributed it to a hot, low-pressure trough sitting west of Vietnam, combined with foehn winds that descend from the Truong Son mountain range and, in doing so, strip moisture out of the air, arriving hot and dry on the leeward side, which is a mechanism that structurally has more in common with the kind of downslope compressional warming we described earlier for heat domes than you might expect, and this isn't a one-off. Earlier in the year, in late March, the Southern Regional Hydrometeorological Center reported heat conditions already developing in Ho Chi Minh City, with Tan Son Nhat reaching 35 degrees Celsius and relative humidity dropping to just 39%. Notably low for a city whose climate is normally defined by its humidity. Forecasters at the time said this would mark the first heatwave of 2026 for northern and central Vietnam, arriving earlier than the long-term average, with Hanoi expected to peak around 36 degrees Celsius during that early season event. And looking ahead across the full season, Vietnam's National Forecasting Center projected, back in April, that northern and central Vietnam would see roughly 2 to 3 heatwaves per month through May and June, with southern Vietnam seeing 1 to 2 per month, though the onset of the southwest monsoon was expected to bring some relief to the south as the rainy season arrived. That same April forecast contained a detail that connects directly back to something we discussed earlier in this video, the El Niño and La Niña transition. Vietnam's forecasters projected that El Niño conditions were highly likely to develop around June 2026 and persist through the end of the year, possibly into early 2027, and warned that this would likely cause rainfall during Vietnam's 2026 rain season to run below normal nationwide, with knock-on effects for water resources heading into the 2027 dry season. Remember earlier, we mentioned that the Washington State Climate Office had noted La Niña conditions transitioning toward neutral by March 2026. Vietnam's own forecasters are now projecting that same broader Pacific system continuing its swing from La Niña through neutral toward El Niño by June, which is again this month right now. Two forecasting agencies on opposite sides of the Pacific Ocean, independently describing the same underlying shift in the ocean atmosphere system, each one translating it into what it means for their own region: rainfall deficits and a delayed, weaker monsoon for Vietnam, drought conditions and elevated heat dome risk for the western United States. So here's the comparison that I think is genuinely useful, and it's not the comparison you might expect. It's not is Portland's heat as bad as Hanoi's heat. By raw temperature, Hanoi's 40.7 degrees Celsius in late May is meaningfully hotter than Portland's forecast 37 degrees Celsius this weekend. The useful comparison is about exposure and adaptation, the same framework we used earlier when comparing the Pacific Northwest to the American Southwest. A resident of Hanoi or Ho Chi Minh City, dealing with their third or fourth heat wave of the season by mid-June, has a level of heat acclimation and lives in a society with infrastructure, daily routines, and public health messaging that has evolved around the expectation of extreme heat as a normal, if increasingly intense, part of the year. The National Center for Hydrometeorological Forecasting's bulletins routinely warn about fire and explosion risk from heat combined with low humidity, about urban heat island effects from concrete and asphalt adding 2 to 4 degrees Celsius on top of the ambient forecast in built-up areas, and about specific risks to the elderly, children, and outdoor workers, all of which should sound familiar, because it's almost word for word the same checklist the National Weather Service in Portland issues, just for a population and a built environment that's had far more practice responding to it. That's the real takeaway from putting these two stories side by side. The Pacific Northwest is, in a sense, going through an accelerated version of an adaptation process that places like Vietnam have already been living through for years, building the institutional muscle memory, the public messaging habits, the infrastructure investments, that turn a dangerous new kind of weather into a recurring seasonal challenge that we have a playbook for. Neither version makes the underlying heat any less dangerous for the people experiencing it. But it does mean that, 5 years from now, if you're watching a video on this channel about a heat dome somewhere in the world that's never had one before, the playbook being referenced, cooling centers, overnight low monitoring, urban heat island mapping, public alerts calibrated to specific vulnerable groups, will likely trace back in part to lessons learned in places like Vietnam that have been dealing with this far longer, as much as it traces back to the Pacific Northwest's hard lesson from 2021. There's also a more direct, if less scientifically glamorous, connection. Extreme heat events like the one unfolding in the Pacific Northwest this week are becoming a kind of bellwether, a leading indicator that gets covered extensively in international media, which means that the kinds of preparedness measures, public health messaging, and infrastructure adaptations that places like Portland and Seattle are working through right now often get studied and referenced by urban planners and public health officials in rapidly growing cities elsewhere in the world, including across Southeast Asia, where urban heat island effects are intensifying as cities like Ho Chi Minh City continue to grow and as green space gets replaced by concrete and asphalt. The cooling center strategies, the overnight low monitoring, the public messaging about checking on elderly neighbors, all of this is becoming a kind of shared global playbook for heat response, refined event by event, and the Pacific Northwest's relatively sudden transition from place that's never needed this to place that's actively building this is itself a useful case study for any city, anywhere that's starting to take heat seriously for the first time. Okay, let's bring this all the way back to the central question of this video, and let's be as precise as we can about what's confirmed, what's forecast, and what remains genuinely uncertain, because that distinction is the entire point of an honest forecast discussion, and it's where we're going to spend the remainder of this video. Here's what's confirmed as of this recording. The National Weather Service office in Portland issued an extreme heat watch on June 9, 2026, at 9:16 p.m. Pacific Daylight Time, covering the Portland-Vancouver metro area, the central Willamette Valley, the lower Columbia River Valley, and the western Columbia River Gorge, in effect from Sunday, June 14th through Tuesday, June 16th. The bulletin specifies dangerously hot conditions with temperatures between 95 and 100 degrees Fahrenheit possible. Separately, broadcast meteorologists in Portland confirmed that the first heat wave of the summer would begin building Saturday, June 13th, with afternoon highs in the low 90s, climbing into the upper 90s on Sunday the 14th, with some locations potentially reaching triple digits. The 7-day point forecast for the Portland area shows a gradual build, Friday near 78, Saturday near 80, Sunday near 92, and then Monday and Tuesday, June 15th and 16th, both near 98 degrees Fahrenheit, with overnight lows around 65, but carrying a 10 to 20% chance of staying above 70. That's the confirmed part. Now here's the forecast part, the part that's based on model projections rather than observed bulletins, and that carries the uncertainty that comes with any forecast more than a couple of days out. The European model, the ECMWF, has been showing 850 millibar temperature anomalies in the range of 14 to 16 degrees Celsius above normal for the June 15th to 17th window. And meteorologists covering this have explicitly noted that those anomaly numbers at that specific atmospheric level are in similar territory to what was observed in 2021. That's a real, model-based signal, and it's the reason this story is getting attention at all. And now here's the genuinely uncertain part, the part where, if you watch 5 different weather channels covering this story, you might hear 5 somewhat different framings, not because anyone is wrong, but because this is exactly the kind of forecast detail where models can and do diverge. The uncertain element is persistence. Will the upper-level ridge associated with this heatwave behave like a multi-day, locked-in heat dome, the kind that produced 2021's catastrophic days-long event? Or will it behave more like a transient ridge that builds over a weekend, peaks for a day or two, and then gets dislodged by the return of more typical onshore flow from the Pacific? As of the most recent commentary we found, meteorologists were explicit that what's missing, at least so far, is the kind of historic, locked-in upper-level ridge that made 2021 the killer it was. The current model runs show a ridge. They do not show that ridge. But so far is the key phrase, because these model runs update multiple times per day, and a forecast that looks like a 1 or 2 day heat spike on Wednesday's model run can look like a 4 or 5 day event by Friday's model run, if the broader atmospheric pattern shifts even slightly. This is genuinely the nature of forecasting heat domes specifically, and it's worth understanding why, because it'll help you interpret any heatwave story you encounter in the future, anywhere in the world. The placement and persistence of an upper-level ridge depends on the broader configuration of the jet stream, and the jet stream, on timescales of 5 to 10 days, is influenced by a huge number of interacting factors, from sea surface temperature patterns in the Pacific to the state of the polar vortex, to smaller-scale disturbances that can nudge a ridge a few hundred kilometers in one direction or another. A few hundred kilometers might not sound like much, but it can be the difference between a ridge that sits directly over Portland for 5 days and a ridge that sits slightly further east over the Rockies, while the Pacific Northwest gets a more typical early summer warm spell with a quicker return to onshore flow. So if you're in the Pacific Northwest right now, here's the calm, practical version of everything we've covered. The confirmed forecast: highs near 98 degrees Fahrenheit on Monday and Tuesday, June 15th and 16th, with overnight lows in the mid-60s and a meaningful chance of staying warmer than that overnight, is, on its own, enough to justify taking heat seriously this weekend, independent of whatever happens with the broader 2021 comparison question. 98 degrees Fahrenheit, sustained over 2 days, in a region with limited air conditioning and limited heat acclimation, is the kind of heat that contributes to heat exhaustion and heat stroke, especially for older adults, for people with chronic health conditions, for outdoor workers, and for anyone without reliable access to a cool space, especially overnight. The practical steps are the same ones that show up in every NWS heat bulletin, and they're worth repeating because they actually work. Stay hydrated, and that means water, not just any beverage, since caffeine and alcohol can both contribute to dehydration. Plan strenuous outdoor activity, if you must do it at all, for the early morning hours before the heat builds. If you don't have air conditioning, identify a cooling centre or another air-conditioned space, a library, a shopping centre, a community centre, and have a plan for getting there, especially if you're elderly or know someone who is. Check on neighbours, particularly elderly neighbours who live alone, because as we discussed earlier, heat doesn't announce itself the way other hazards do, and a wellness check is often the only thing that catches a developing problem before it becomes a medical emergency. And if you're near rivers, lakes, or the coast and looking for relief in the water, remember the cold water shock warning. Water temperatures in this region in mid-June are still cold enough that jumping in suddenly, especially after being overheated, carries its own risk, so a personal flotation device and a gradual entry into the water are both worth the extra few minutes. For the wildfire angle, the red flag warnings tied to low humidity and wind gusts up to 30 miles per hour mean that this is also a moment to be especially careful with anything that could spark a fire, and if you live in or near the wildland-urban interface in Oregon or Washington, This is a good weekend to make sure you know your evacuation routes, even if nothing happens. The 2021 event is a stark reminder of how quickly an extreme heat event can transition into a wildfire event, sometimes within 24 hours, as happened in Lytton. And for everyone else, everyone watching from outside the Pacific Northwest, including our viewers here in Vietnam, the takeaway isn't something terrible is definitely about to happen. It's something more useful than that, actually. It's a real-time demonstration of how a region adapts in real time to a changing baseline. 5 years ago, the Pacific Northwest had essentially no playbook for a heat event like 2021. This week, that same region has an extreme heat watch issued 5 days in advance, specific guidance about overnight low temperatures and their public health implications, coordinated messaging about cooling centers and cold water shock, and a public and a media that immediately reaches for the 2021 comparison the moment a forecast model shows similar numbers at the 850 millibar level. That's what adaptation looks like. Not the absence of extreme events, but a system that's gotten faster and more specific at recognizing them, communicating about them, and preparing for them, even while the underlying climate trend that makes these events more frequent continues in the background. Completely indifferent to how well prepared any of us are, there's one more piece of context worth adding here, because it helps answer a slightly different but related question. Not is this week as bad as 2021, but how often is the Pacific Northwest having these conversations now compared to before? And the honest answer is, a lot more often than it used to. Take last summer, July 2025. Western Washington and Oregon, including Seattle, Portland, the Willamette Valley, and the Columbia River Gorge, went under a heat advisory through a Wednesday night as what was described as a short but intense heat wave swept through. Portland was forecast to hit 92 degrees on the Tuesday and 97 on the Wednesday, before dropping back into the mid-80s by the weekend. Seattle was forecast for 86 on Tuesday and 91 on Wednesday. Those numbers on their own are basically what this week's forecast looks like. A short, sharp heat event, a couple of days in the 90s, then a return to more typical conditions. Not catastrophic, but notable enough to warrant a heat advisory and media coverage in a way that 20 years ago a couple of days in the low 90s in Seattle simply wouldn't have. And here's the detail from that July 2025 event that connects directly back to something we discussed earlier: overnight lows. The reporting on that heatwave specifically highlighted that even the nights would stay warm, prolonging the potential health effects of the heat, and it cited a broader climate analysis showing that average summer overnight lows have risen measurably across the region. Seattle's average summer low up by 2.9 degrees Fahrenheit, Portland's up by 3.7 degrees, Yakima's up by 4.3 degrees, and Spokane's up by 5.1 degrees compared to historical baselines. Remember what we said earlier about overnight recovery time being one of the most underappreciated factors in heat mortality? This is that trend in hard numbers. It's not just that daytime highs are creeping up, it's that the nights, the part of the day when an unacclimated, unair-conditioned body is supposed to get its only break from the heat, are warming even faster in some of these cities than the daytime highs are. Now go back to 2021 itself for one more data point, because there's a specific number from that event that, when you hear it now, in the context of everything we've just discussed about overnight lows, lands differently than it did at the time. During the 2021 heatwave, the overnight low at Portland International Airport on one of those nights came in at 73 degrees Fahrenheit, breaking the previous record for the warmest overnight low ever recorded at that location, which had been 71 degrees, set back in 2015. Seattle-Tacoma International Airport saw a similar story, a low of 73 degrees, breaking that location's previous warmest low record of 71, also set in 2009. A National Weather Service meteorologist at the time noted that the following morning's low was expected to come in around 75 degrees, which would have set yet another record for warmest overnight minimum, 75 degrees Fahrenheit, as an overnight low in Seattle, for a city where the entire cultural and architectural identity has, for over a century, been built around the assumption that nights cool off. That's not just a hot day followed by a normal night. That's a fundamentally different climate regime showing up, for a few days inside a built environment that was never designed for it, and that more than the headline daytime maximums is probably the single number from 2021 that best captures why the event was as deadly as it was. So, with all of that laid out, the confirmed forecast for this weekend, the model-based signal that's drawing the 2021 comparisons, the genuinely open question about ridge persistence, the broader anomalous spring across the West, the power grid context, the space weather context, the Vietnam and broader Pacific connection, The Cascadia question addressed and set in its proper place, and now this longer-term trend of rising overnight lows that's reshaping what normal even means for summer nights in this region. Where does that leave us? It leaves us, I think, in a place that's more nuanced than either nothing to worry about or here we go again. The forecast for June 14th through 16th, 2026 as it currently stands calls for a genuinely hot, genuinely consequential heat event, highs near 98 degrees Fahrenheit over 2 consecutive days, an extreme heat watch in effect, real public health risk for vulnerable populations, and a non-trivial chance that overnight lows fail to provide adequate recovery time. That's serious on its own terms, full stop, independent of any comparison to 2021. At the same time, the specific combination of factors that made 2021 a once-in-10,000 years event, that historic, locked-in omega block ridge with anomalies exceeding 4.5 standard deviations from normal, is not, as of this recording, what the models are showing for this week. The anomaly signal at the 850 millibar level looks similar. The persistence signal does not, at least not yet. If you're in the region, that means this weekend deserves real preparation, not panic, but the kind of preparation that's become standard practice since 2021. Hydration, shade, checking on vulnerable neighbours, having a cooling plan, being careful with anything that could spark a fire. If you're watching from elsewhere, including from here in Vietnam, it means watching this as a case study, both in how heat domes form and intensify, and in how a region that, 5 years ago, had almost no playbook for this kind of event, now has bulletins, watches, and public messaging arriving days in advance, shaped directly by the lessons of 2021. And if the ridge does intensify over the coming days, if Friday's or Saturday's model runs start showing that locked-in, multi-day signature that's currently absent, we'll be back with an update, because that would change this story considerably. For now, the honest summary is this. The ingredients for something serious are present in the broader pattern. The immediate forecast justifies real caution, and the specific ingredient that turned 2021 into a historic catastrophe, persistence, remains the open question. Before we close, I want to widen the lens one more time, because the Pacific Northwest isn't the only place on Earth that's had to learn this lesson the hard way, and putting this week's story alongside the others helps put a number on something that can otherwise feel abstract. The actual cost in human lives of a stuck ridge of high pressure go back to the summer of 2003 in Europe. An omega block, the same basic atmospheric shape we described earlier, a high-pressure ridge flanked by 2 troughs, refusing to move, settled over Western Europe and held temperatures around 38 degrees Celsius, about 100 Fahrenheit, for roughly 2 weeks straight across much of the continent. The peak temperature recorded anywhere in Europe that summer was 47.3 degrees Celsius, at a location called Amareleja in Portugal on August 1st. But it was the duration, not just the peak, that made the 2003 European heatwave one of the deadliest weather disasters in modern European history. Researchers using excess mortality methods, comparing actual deaths during the heatwave to what would normally be expected for that time of year, arrived at a figure that's almost hard to say out loud. More than 70,000 excess deaths across Europe that summer. France alone accounted for somewhere between roughly 14,800 and 19,000 of those deaths, with refrigerated trucks reportedly used to store bodies as morgue capacity in parts of the country was overwhelmed. Italy's toll has been estimated at around 20,000, Spain close to 13,000, Germany around 9,500, the United Kingdom around 2,000. A 2004 attribution study, one of the very first of its kind, a field that's grown enormously since, concluded that human-caused climate warming had at least doubled the likelihood of an event like the 2003 European heatwave occurring. A separate analysis later found that 506 of the roughly 735 summer deaths recorded in Paris that year, and 64 of the 315 in London, were directly attributable to the heatwave being intensified by human influence on the climate, meaning that without that warming, those specific deaths likely wouldn't have happened. And here's the part that connects most directly to everything we've discussed about the Pacific Northwest tonight. A study published just within the past year, November 2025, modelled what a 2003-style heatwave would do if it happened again today, with the additional warming that's accumulated in the 2 decades since. The finding, a repeat of that same weather pattern today, would be expected to kill nearly 18,000 people across Europe, and at 3 degrees Celsius of warming above pre-industrial levels, a level the planet is on a trajectory to approach later this century absent significant emissions reductions. A similar event could cause around 32,000 excess deaths. One of the study's co-authors, a Stanford professor, put it in stark terms, Events like this could become as severe as some of the worst weeks of the COVID-19 pandemic by mid-century on a recurring basis. Why does this matter for tonight's story? Because it's the same mechanism, the same shape, the same vulnerability profile, a population and a built environment calibrated for a climate that no longer fully exists, hit by a stalled ridge of high pressure that traps heat for days at a time, with the elderly and those without adequate cooling bearing the overwhelming majority of the cost. The 2003 European event was at the time considered so statistically extreme that researchers initially calculated it as roughly a 1 in a million year occurrence under the pre-warming climate. The 2021 Pacific Northwest event was independently calculated, using similar attribution methods, as somewhere between a 1 in 1,000 and a 1 in 10,000 year event. 2 different continents, 2 different climate zones, 2 different population profiles, and in both cases, the statistical machinery that's supposed to tell us how often something should happen got broken by an event that happened anyway. Within the span of less than 20 years of each other, this is the pattern that researchers mean when they talk about heat domes, becoming more frequent and more intense under a warming climate. Not that every heat wave is now a 2003 or a 2021, but that the tail of the distribution, the truly extreme end where these once-in-a-millennium events live, is being pulled closer to the centre of the distribution. Events that used to require a near impossible alignment of atmospheric factors are now reachable with a more ordinary alignment, simply because the baseline temperature everything is operating from has shifted upward. A ridge that, in 1990, might have produced a memorably hot week now has the potential, given the right additional ingredients, to produce something categorically different, and the gap between memorably hot and categorically different is shrinking, which brings us back one final time to this week's forecast, and to the honest framing we've tried to maintain throughout this video. 98 degrees Fahrenheit for 2 days in Portland is not 2003's 2 weeks at 100 degrees across Western Europe, and it's not 2021's 116 degrees with a national record falling 3 days running in Lytton. But it's also not nothing, and the reason it's not nothing is precisely because of this broader pattern. The same warming trend that turned 2003 from a 1 in a million year event into something that could now kill 18,000 people if it recurred, and that turned the specific atmospheric configuration of 2021 into a once in 10,000 years event that happened anyway, is the same trend sitting underneath this week's forecast. The same trend that's pushed Seattle's and Portland's average summer overnight lows up by several degrees. The same trend that NOAA's Climate Prediction Center has been flagging since March as favouring above normal temperatures across almost the entire western United States this spring and summer. None of this means doom. It means context. It means that when a meteorologist this week looks at an 850 millibar anomaly map and says, "This looks like 2021 at the mid-levels," that observation carries weight not because 2021 was a fluke that's unlikely to recur, but because the conditions that produced 2021 are becoming, gradually, less rare, even if this particular week, this particular ridge, doesn't end up matching that full signature. So here's what I want to leave you with tonight. 5 years ago, almost to the week, a region known for its rain watched its all-time temperature records fall by 4, 5, 6 degrees in a single day, watched a town named Lytton set and reset a national heat record 3 days running before it burned to the ground, and lost hundreds of people to a hazard that, on the surface, doesn't look like a hazard at all. Just heat, just sunshine, just a few days without a cloud in the sky. This week, the same region is watching the sky again, watching the models, watching the same atmospheric layer that gave the first warning back then. The numbers aren't identical, the story isn't finished, but the region is watching, and maybe that, more than any single temperature reading, is the real measure of what's changed since 2021. If you're somewhere that's also seeing unusual heat right now, wherever you're watching this from, I'd genuinely like to know. Drop a comment with where you are and what the last week has looked like where you live, because if there's one thing this whole story illustrates, it's that these patterns don't stay contained to one region. They ripple outward, across an ocean, across a hemisphere, in ways that connect a forecast bulletin from Portland, Oregon, to a rice paddy in the Mekong Delta. Whether anyone involved realizes it or not, we'll keep tracking this through the weekend. Stay cool, stay informed, and we'll see you in the next one.